Okay, so in this second part of the talk, I'm going to talk about some very much recent results on free boundary minimal surfaces in the Unit 3 ball. So this is a rough outline for the talk. So notice that it will be rather similar in terms of the structure to the first talk. Okay, so it would be nice if we can make a comparison between the results for minimal surfaces in the sphere and the analogous results and questions for free boundary minimal surfaces in the ball. Right. So first of all, we're going to denote by B3 the unit three-dimensional ball inside Euclidean space. And if we have a surface sigma inside the ball, we say that this is a free boundary minimal surface in the ball. If first of all, this is a minimal surface, okay, and it also satisfies an additional free boundary condition. Okay. So these three equivalent statements would be also defining a free boundary minimal surface in the ball. So the first is a geometric statement again, because the interior is a minimal surface, so mean curvature vanish as before. But now the free boundary condition corresponds to the fact that the surface has to hit the boundary, which is a two-sphere, orthogonally along the boundary of sigma. Okay. All right, so this is the geometric free boundary condition. And variationally, we can actually characterize it as that the surface is in fact a critical point to the area functional. But now the surface has a boundary, but the boundary is always constrained to lie on the boundary sphere. Okay. It can move, but it can only move on the boundary sphere. Okay, so if we look at this variational problem, complete the first variation formula. All right, keeping that the boundary is fixed, is constrained on the boundary sphere, then the first version formula gives you an additional term, okay, which is coming from the boundary movement. Okay, so you see that this will always vanish for any x which is tangential to the boundary sphere, only when eta is perpendicular to the boundary sphere. So this free boundary condition would be achieved when the eta is parallel to the position vector in this case. Right? So this in turn would be giving you a third equivalent definition above, which is saying that the coordinate function now is not an eigenfunction, but is indeed harmonic, okay? Because now the mean curvature is 0 in the interior as a minimal surface of R3. And now the free boundary condition corresponds to a Robin condition. Okay? So if you look at the outward normal derivative of the coordinate function, this is equal to the coordinate function itself on the boundary. So this condition here is just precisely this condition. Okay. All right. So again, what are some of the simplest examples in this case? All right. So the simplest example is given by the so-called equatorial disk. So if we look at one of the coordinates, set it to 0, then you're going to get, so in this picture that I'm drawing, so like x3 in this direction, then you look at the equatorial one. So this is of course a flat minimal surface, just a flat plane, and it hits the boundary orthogonally because it's equatorial. So this angle is 90 degrees. So this example is flat and totally geodesic. Okay, all right, not too interesting. So the next one, which is very interesting, is given by a rotationally symmetric example called a critical catenoid. So we know that rotationally symmetric minimal surfaces in R3 are given by complete catenoids up to a scale in the translation. Okay, so in fact, once we translate it such that the center passes through the origin, there's a unique scale given by this R critical, which sort of fits the catenoid into the ball in a way that it hits the boundary sphere orthogonally. Okay. So this is called a critical catenoid. So there's a unique scale which does that. And in fact, variationally, this is the maximally stable region of the complete catenoid in R3. Okay. We call that the catenoid in R3 has index 1. So you should be able to find a region big enough that it will become unstable. And small enough that it will be stable. So there's sort of something in between which makes it just marginally stable. And this is the domain given by the critical catenoid. Okay, so here I list some very basic properties about general free boundary minimal surface in the ball. Okay, so first of all, the minimal surface has to be so-called proper, which means that the minimal surface, if you look at this, will only hit the boundary sphere at the boundary of the surface. Okay, that means, for example, you cannot have a surface that has an interior touching the boundary like that. Okay, this is because of the maximum principle, as the coordinate functions are harmonic functions. So this is just a direct consequence of maximum principle. So secondly, there's a relationship between the area of the minimal surface and the length of the boundary. Okay, so 2 times the area of the minimal surface would just be equal to the length of the boundary. So this is very useful because this sort of means that if you look at the area of the minimal surface, you can sort of equivalently measure by looking at the length of the boundary. Okay. So for example, if we try to characterize the minimal surface by the area, you can equivalently characterize it in terms of the boundary length. Okay. So this can be shown by a very simple integration by part argument. Okay. So because the xi are harmonic, so if you look at this, this is of course equal to 2, right? So I'm sorry, that's actually equal to 4, right? So this is a square there, so equal to 4. So this integrate will give you 4 times the area of the surface. But if you do integration by parts, so you can change this into a boundary integral of the outward flux. Okay. But now because the free boundary condition tells you that dxi d eta is equal to xi, so you get just this expression here with a 2 because of this square, right? So now, but because the boundary of sigma lies on this unit sphere, so this part is in fact equal to 1. So this integral just gives you 2 times the length of the boundary. So you cancel out by 2 on both sides, you get the formula. Right. Okay, so remember that for minimal surface in the sphere, you have the property that it is balanced. Okay, the center of mass of the whole surface is at the origin. So in this case, you actually have a similar balancing condition, but it's only on the boundary of the sphere. Okay, so sorry, this xi should be in the integrand. Right? So if you take the average of the coordinates of the boundary, then you always get 0. So the center of mass for the boundary is located at the center. So you can see it from the picture here. So this is the boundary, center of mass is located at the center, and this is the boundary. So it consists of 2 circles. This is the center of mass. Finally, because the ball is simply connected, so any embedded hypersurface inside is automatically orientable. Right? So this is similar to the case for minimal surfaces in the ball, in the sphere. So what are some examples and how do we construct them? So it turns out that it is even harder to construct examples compared to the case for the sphere. Right? So we are interested in asking, other than the equatorial disk and the critical catenoid that we have just talked about, can we find other examples? Okay. Of course, we are looking at compact examples, maybe embedded, maybe immersed. Okay. All right. So we call that in the case of closed minimal surface in S3, right? We have a lot of examples constructed by Lawson. In fact, any orientable surface can be realized as an example. So in our free boundary setting, we also want to ask a similar question. So is there any topological obstruction of finding a certain minimal surface with that topology inside the 3-dimensional ball? Right. Well, it's even unclear whether this question is affected by whether we allow self-intersection or not. Okay. So in the past about 10 years, there are many new existence results of free boundary minimal surfaces in the ball, but we are still quite far from fully understanding this question in light of the results of Lawson. For example, up to date, we don't have an example of free boundary minimal surface in the ball whose genus is 1 and have only 1 boundary component. So this we have a genus 0 example and 1 boundary component given by the disk, and we have a genus 0 example with 2 boundary components given by the critical catalog. So the next the other simplest one is genus 1, 1 boundary component. Even for this simple topology, we don't know any example exists or not. Okay. And as I said, it's unclear whether the question makes a difference, whether we allow self-intersection. So this is complicated by the fact that unlike the case of closed immersed minimal tori in the 3-sphere, we don't have any non-embedded example of free boundary minimal surface in the ball. Right? So all the known examples so far are embedded. So how do we construct examples? So the first examples were given by considering extremal eigenvalue problem for the stack of eigenvalue. So let me briefly talk about what the stack of eigenvalues are. Okay, so this has something to do with the Dirichlet-to-Neumann map, which can be actually defined on a general compact Riemannian manifold boundary. Let's call this M. So the thing is that if we look at this picture here, okay, so I'm going to specify a Dirichlet data on the boundary given by U, all right? So this is a compact Riemannian manifold boundary, so I can solve for harmonic function inside. So this is called U hat with Dirichlet data given by the prescribed U. And then once I get this harmonic extension, I can compute the outward normal derivative of this harmonic function at the boundary. So in the end, I'm going to be inputting a Dirichlet data U on the boundary, and then output a Neumann data on the boundary. So this is why it's called a Dirichlet-to-Neumann map, denoted by L here. So it turns out that this Dirichlet-to-Neumann map behaves very much like the half Laplacian. Okay, so this is indeed this is non-local pseudo-differential operator, but this is elliptic, self-adjoint, and has a discrete spectrum. So this the spectrum also starts with 0 corresponding to constant function on the boundary, which extends to constant function interior. Over normal derivative is of course 0. Okay. So the first non-trivial one is given by sigma 1. Okay. And this spectrum actually goes to positive infinity at a certain rate. So we can ask a very similar extremal eigenvalue problem like the case of closed surfaces. Okay. So in this regard, a very old theorem of Weinstock in 1954 studied this problem on the disk. Okay, so if we look at all the possible metric G defined on the disk, right? If you look at sigma 1 suitably normalized, okay, so this is multiplied to the length of the boundary with respect to the metric G, just to make it scale invariant. So basically, if you try to maximize sigma 1 up to some normalization, the maximum is equal to 2 pi, which is achieved uniquely by the planar round disk. Okay, so the sigma 1 is equal to 1 in that case, and the length of the boundary of the round disk is 2 pi. So of course, then other than the disk, one can ask, okay, what about other topological types? So Fraser and Sheng studied this problem in 2011 and proved a similar coarse upper bound like what Yang and Yao did. So if you look at sigma 1 times the boundary length, this is always bounded by a constant C, which depends only on the topology, but independent of the metric. So this coarse upper bound allows us to set up an extremal eigenvalue problem by trying to maximize this quantity, okay, among all smooth metrics. Okay. So this will be called, if it exists, will be called an extremal metric G star. So whether we can understand the geometry of this extremal metric is an important question. So in this paper of Fraser and Sheng in 2016, so they gave a very useful characterization, very much like what Dirichlet did for closed surfaces. So they show that if the extremal metric, which achieved the maximum, is a smooth metric, then up to a conformal diffeomorphism, you can actually realize this metric as a free boundary minimal surface inside a ball, a unit ball, which may have higher dimension. Okay, so this gives again, like what Dirichlet did, this gives a sort of a direct link between the extremal stack of eigenvalue problem with free boundary minimal surfaces in a ball. which may be of higher codimension. So so this problem actually is quite hard again. Okay, but Fraser and Shing managed to solve this problem, at least in the genus 0 case. All right. So unlike the case without boundary, the genus 0 case is only the sphere. All right, that is already solved by Hirsch. Now, because you might have a lot of boundary components. Okay, so genus 0 surfaces, there are still infinite many of those. Okay, so they show that for each of this genus 0 surface with any boundary components you might have, the extremal metric is achieved by a smooth metric. Okay. So by their theorem before, this would imply that they can be realized as free boundary minimal surfaces inside the ball. And they show that actually this ball that realized them as a free boundary minimal surface can be chosen to be dimension 3. So these are the sort of the schematic picture, heuristic picture of what they will look like. So the simplest one has one boundary component. It's just a disk. So that's the equatorial disk. All right. So this is the first example that we have seen. So the second example has genus 0 and 2 boundary components. So topological is an analyst. So this is actually given by the critical cat-like. Right. So this was actually done in their 2011 paper. And for more than 2 number of boundary components, they show that smooth extremal matrix exists, and when the number boundary components goes to infinity, the picture looks roughly like 2 disks joined together by some half-catenoidal bridges near the boundary. So it looks roughly like this. So in the limit, it converges to 2 times the disk with multiplicity 2. So other than this genus 0 example, there's only one, as far as I know, explicit extremal metric which is known to exist. And this is given on the Mobius band, called the critical Mobius band. And this can be realized as a free boundary minimal surface in the 4-dimensional ball, okay, embedded there, okay, but not in 3 dimension. Okay. Because we know that, well, Mobius band is not orientable. So it cannot be embedded inside the ball, okay, of dimension 3. Right? So the smallest dimension can be embedded is dimension 4. Right? So of course, one can ask, okay, what happens for higher genus surfaces? Okay, so this is a very difficult question, and I just want to make a remark that there's a very recent paper by Mathiasen and Petraitis, which solve this problem based on a few of their previous works. Okay. So they show that a smooth extremal metric would exist, although we don't know explicitly what it should look like. Okay, so one can also go in the other direction of using gluing construction to construct new examples. So in the joint work with Capoleus, we proved the following example exists. Okay, so these examples first of all, has very high genus because of the gluing construction, and they have 3 connected boundary components. So they are sort of roughly like the, if you know, the Koster-Hoffman mixed surfaces, which are complete minimal surfaces in R3, finite total curvature, and finite genus. So they are sort of similar to those for the higher genus ones. Okay. They also have a dihedral group of symmetries given by reflection about some vertical planes, and they also are symmetric about some horizontal lines passing through the origin. Okay. So, so the basic idea is that is a desynchronization method. So you take the 2 known examples, okay, that we had. So we have the disk, and then we have the catenoid here. All right. So of course they intersect along some circle here, drawn in green. So the idea is that I want to, again, replace the circle of intersection, a neighborhood of that, by some smooth surface that resembles bending of a circle surface. Okay, and then we correct it to an actual surface by PDE approach. So notice that we have to sort of be careful about like keeping the boundary orthogonal in this process. Okay. But we can do it, and you can see that as the number of genus which concentrate around the circle of intersection here goes to infinity, then this will go back to this original picture, which is the union of the disk and the catenoid. Okay, this is actually in the Hausdorff sense. So there are also other examples constructed by gluing that has been done in the past few years. So that's a doubling construction done by Foha, Packard, and Solotarev in 2017. So the example would look roughly like this, kind of like the higher connected components genus 0 example of Fraser and Shane. Right? They can also do it by adding in genus in the origin, so they will have genus 1. Okay. So there's also a very interesting tripling construction that has been done by Capellas and Rigil. So what they consider is that instead of looking at the 2 copies of the disk, okay, one can actually consider 3 copies of the disk, and by suitably joining them, you can actually find one which has connected boundary. Okay, they will also have high genus for the surface. Okay, so but they only have one connected boundary component. So in an ongoing project of Capellas, we're also trying to do some less symmetric desynchronization method. For example, if you look at intersection of 2 disks, then they will intersect along a line, right? So we would like to desynchronize it along this line. We can also consider more than 2 disks, which is symmetrically arranged about the origin, which intersect along a line. Okay? So this will need the model of higher order Sheff to desynchronize the picture. So this is much harder because the amount of symmetries we had is much less than the previous picture where we had the O2 symmetry. Here we don't get that O2 symmetry. So we have to be careful about choosing the choice of scale along the directional intersection. So finally, there's also another line of approach using min-max method. The first ones are obtained by Ketova in 2017 using an equivariant min-max. Okay. So he was able to construct 2 classes of examples. One uses the symmetries of the Platonic solids, very much like the Kakia, Pinko, Stirling examples. So in this case, he constructed only finitely many of those. Okay, so these are all have genus 0 and has this number of ends. Okay, all right. So he also, by considering other symmetry groups, he also construct genus 0 examples of any number of boundary components. Okay. So they will have the same topological types of the Fraser Shane surfaces, and they also constructed examples which are topologically the same as the surfaces that I constructed with capital layers. So the basic question here is that, well, these examples constructed by min-max has the same topology as the ones obtained by Fraser and Shane using the extreme eigenvalue problem and gluing methods of capital layers and myself. So are they actually the same examples? Okay, that they just differ by congruence of the ball? So this is an open question. So next, a very recent paper by Calato, Friends, and Schultz appeared on arXiv this year, used a continuous min-max theory developed by myself in 2015, and they seem to have constructed new examples which have only one connected boundary component and have arbitrary genus. So this genus here can be very small. Okay, so this is a very interesting paper. So of course, we are also interested in like whether these examples, when the genus is high, whether they are congruent to the ones constructed by Capellas and Rigil because they had the same topology. Okay, so finally, I would like to mention some uniqueness results and classification results for free boundary minimal surfaces in the ball. So as in the case for minimal surfaces in the sphere, we can also look at the moduli space. All right, now we have to fix the topology of the surface, which consists of the genus G here, and also the number of boundary components K. Okay. So this will be denoted by MGK, the moduli space of all such example of this particular topology. So notice that in this case, the isometric group B3, of course, would create the ambiguity, but this is also a compact group. Okay, so this is just O3. Okay. So in a joint work with Fraser, in 2014, we proved a smooth compactness result for this moduli space, similar to the ones obtained by Choi and Sheng for closed minimal surfaces in the sphere. So we show that this space, this moduli space, MGK, is also compact with respect to the smooth topology. Right. So of course, we can also formulate a conjecture that maybe modulo the ambient isometry, this is indeed a finite set. Okay, but so far we don't have any more progress towards this other than this theorem. Okay, but of course we can also ask for classification results in terms of topology, Mos index, and area, just like what we have seen in the first talk. So in terms of topology, Nietzsche proved the first uniqueness result in 1985. So if we just consider a minimal disk, okay, the topology is a disk, even you allow immersed surfaces, then the only example is the equatorial disk. So this is in line with Armgren's result. Okay, so if you have a minimal disk, it has to be equatorial disk. In fact, this result also in high dimension as well, surprisingly. So this was also a result of Fraser and Sheng. And other than the disk, we can ask, okay, what about the next topological type, like the annulus, right? So this is sort of going to be analogous to the Lawson's conjecture for the minimal tori in that case. So we ask the following conjecture, whether if you consider only free boundary minimal annulus embedded, okay, so embedded may be important or not, we don't know, okay, because we don't actually have a example of immersed free boundary minimal annulus up to now. But let's say, okay, we assume embedded is a free boundary minimal annulus, whether it must be the critical ctenoid. Okay, so this is the conjecture. So this conjecture today, to my knowledge, is still open, but there are already some partial results along this direction. So my graph proved this is true if we assume that the surface is symmetric about reflection, about the coordinate planes. Okay. And just very recently, a couple of weeks ago, Bob Kunstner and McGrath showed that this is also true if we just assume the surface is symmetric with respect to the antipodal map. Okay. Then this has to be the critical ctenoid. So also a very recent result by Li and Yong set up this problem, which is linked to a PDE near-field equation. So this is also a very interesting idea, and I think Yong is also giving a talk on this. Okay, in this online event. So I'll just refer you to the talk. Okay, so the next thing is about the Mos index. So in this case, if you look at the second variation, because you have a boundary, you also have a boundary term in the second variation given by this. So in fact, this coefficient is a 1 here, which reflects the boundary principal curvature of the sphere. Okay. So, but you can still define the number of negative eigenvalues of this symmetrical bilinear form to be the Mos index of sigma. So it is again an easy calculation that the equatorial disk has index 1. Okay. And they can be shown that they are the only ones with index 1. So remember that in the closed case, Urbano proved that the next smallest index is 5, and that's only achieved by the Clifford torus. So now the conjecture here is that whether the critical ctenoid achieves the next smallest index. Okay. In fact, the index has been computed to be 4. Right. So this was some independent result of Tran, Smith, Joe, and De Vere. So they proved that the critical ctenoid has index 4. So now the problem remains to show that whether this is the only example with index 4, sort of to complete classification result analogous to Urbano's result. So far, this is still not solved yet, but the problem has been solved by Tran if you assume that the minimal surface is topologically annulus. Then we know that this is topological annulus and index is equal to 4, then it has to be critical ctenoid. Actually, if you assume that it's topological annulus, then index equal to 4 implies that the first stack of eigenvalue has to be 1. So by an earlier uniqueness result of Fraser and Sheng, then it has to be a critical cat node. Okay. But this is still not known. If you don't assume a priori this is an annulus topologically, whether you can prove that this is a critical cat node. So this is the key problem there. So of course, and a related problem is that whether we can compute the Mos index of the other examples that we have talked about before. Okay, so this is not an easy task actually. So regarding characterization in terms of area, this is even less known. Okay, so the only results that we have so far is results by Fraser and Sheng in 2011, which they proved that the equatorial disk is the one with the smallest area. Okay. In fact, it's also holds in higher dimension, which was extended by Brendel. So remember that in the case of closed surfaces in S3, we know that other than the great equatorial two-sphere, the Clifford torus is the next one with smallest area. So this is related to the Wilmot conjecture solved by Marquez and Nevis. So we in this case we can ask whether other than the equatorial disk in the free boundary setting, whether the critical catenoid achieve the next smallest area. Okay. So this in fact is related to the Mos index characterization problem that we just have mentioned above. Okay, so one in fact one has to first solve that problem before we can handle this problem. If we have to use a min-max approach to do that. Okay. There's also a related question formulated by Fraser and Sheng, which is the following. So if you look at the free boundary minimal surface in the ball, right, whether it maximizes area if you conformally change it by the ambient diffeomorphisms. Okay. So actually a similar, so this is related again also to the Mos index characterization, because in the case for the closed minimal sphere, closed minimal surface in the sphere, this is true. Okay, so if you take a minimal surface in the sphere, change it conformally, then the area would decrease. Okay. Now the same property, we don't know whether this holds for free boundary minimal surfaces in the ball. Okay, but actually what Fraser and Sheng showed that a similar result does hold for the boundary length of the surface. Okay, so the boundary length does maximize under ambient and also conformal diffeomorphisms. But notice that this still is not enough to imply that the area is also maximized in the conformal orbit. Okay, because even though for a minimal free boundary minimal surface, there's a relation between the boundary length and the area. But if it's not minimal surface, then there's no obvious relation between the boundary length and the area. Okay, so we don't. Fraser-Sheng's result does not immediately imply the question above. Of course, this may be related. Okay, so so in terms of area, there's also this free boundary minimal, a free boundary min-max theory that Shinjo and I developed a few years ago. So we can look at the volume spectrum in that case for the ball, where the width will be achieved by free boundary minimal surfaces. Okay, so the problem is analogous to the Wilmot conjecture is whether we can compute the spectrum of the three-dimensional ball at least on the lower end. Okay, so a conjectural picture is that the first three of them would be given by given by the equatorial disk, and the fourth one would be given by the critical catenoid K, the area of the critical catenoid. Yeah. So finally, I would like to mention a conjecture of similar to Yao's conjecture for closed minimal surfaces in the sphere. Okay. So so remember this relevant case is now the stack of eigenvalue. Okay, sigma 1. So we recall that if I have a free boundary minimal surface in the ball, then the coordinate function satisfies PDE. Okay, so this is actually harmonic with respect to the intrinsic Laplacian, and the our normal derivative of the coordinate function is equal to xi itself. So in terms of the Dirichlet-to-Neumann map, so you have a harmonic extension, our normal derivative is itself. So that means sigma equal to 1. So this 1 here that appear in front of xi is a stack of eigenvalue. So the question is like this stack of eigenvalue, whether this is the first one. Okay. So we actually conjecture that this might be true. Okay. That if we look at any compact embedded free boundary minimal surface, so embedded might be important, just like the Yau's conjecture. Whether all of these examples, embedded examples, have sigma 1 equals to 1. Okay. So this conjecture is still open again, all right? And what we have proved so far with Fraser is that sigma 1 is at least 1/2. Okay, so this is similar to what Choi and Wang obtained in the closed case. And if we assume symmetries, Peter McGrath proved that in 2018 that this is true if that your surface is embedded and has reflection symmetries about coordinate planes. Okay. So in this recent paper of Kunzler and McGrath, they actually relaxed the symmetry assumption to just antipodal symmetry. All right. So they using that they can verify a few other examples that has been known up to date. But the natural question still remains, like at least whether we can verify this conjecture for all these examples that we have known so far. Okay, so this is still there seems still some work in progress along this direction. Okay, so this is all I want to talk about for these two parts of the talk. Thank you for your attention.